Okay, let's go ahead and get started. So we've hit a sort of natural breakpoint in the topical coverage of the class. In that we spent the last several weeks talking about recursion, and in particular building up to talking about dynamic programming, which is one of the biggest. Hang on. Let's try this one. Good. One of the most important and most confusing paradigms for designing and analyzing algorithms. For the next several weeks, I want to talk about the other one. Okay, so the two things that are probably most difficult to designing non-trivial algorithms is, one, being able to think effectively about recursion, and two, being able to model things as graphs and compute things on those graphs efficiently. And I'm going to spend a lot of time talking about specific graph algorithms, but the specific algorithms themselves are not necessarily where the bottleneck is in terms of algorithm design. I'm going to show you Dijkstra's algorithm, for example, which hopefully all of you have seen before. Partly, we want to walk through it a little bit more carefully and a little bit more formally and understand how it works. But partly, but mostly you're going to be using Dijkstra's algorithm as a black box. So you need to understand the algorithm well enough to know when it can be used and what it is supposed to be used for. But we're really going to be spending a fair amount of time doing modeling, taking some problem and rephrasing it in terms of graphs, and then applying an algorithm that you've seen in class. And the algorithms that we're going to look at can also fall into the same categories that we've seen already. Some of them are just bare recursive algorithms or backtracking algorithms. Some of them are backtracking algorithms with a little bit of bookkeeping to keep from repeating yourself. Some of them are dynamic programming algorithms. Some of them are greedy algorithms. But the most significant bit here is not going to be so much on the recursion as on the kinds of structures that in the graphs that the algorithms are exploiting. Okay? So when we're starting out today, most of what I will talk about today will be completely review. It's just basic definitions, data structures to use for representing graphs, and some standard graph traversal algorithm. But again, I want to go over this partly so that we just are all on the same page with vocabulary, and partly because some of my usage is very, very slightly non-standard. So this is a graph. The thing on the screen is a graph. I said that correctly. The thing on the screen is a graph. This is also a graph. It's called the subgraph of the big one. But this thing up here that has 9 vertices, and how many is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 edges. Just again, so that we're all on the same page, what is the singular of vertices? Node. If you say vertice, you owe me $1. If you say matrice, you owe me $1. If you say indice, you owe me $1. The correct terms are node, array, and integer. Vertex, matrix, index. I am dead serious about you owing me $1. I will collect. We will write, you owe us $3 on the front of your homework. If you write that on a homework or on an exam, expunge it from your brain. If you have trouble remembering that the singular is a vertex, call it a node. Okay? Just use node. No one ever, gets confused about what the plural or singular of nodes is. Okay, so this is a graph that has 9 vertices or nodes and 13 edges. Edges are sometimes called by other names, links or arcs or paths or a few other things like that. Is it 9 vertices? 13 edges. This graph has 2 components. What it means for a piece of the graph to be a component is from any vertex in that component to any other, there is a path from the first one to the second one. So, for example, I know that A and F are in the same component because I can find a path in this graph from A to F. Okay? So a path is a special subgraph where you can think of it as alternating between vertices and edges, and you're never allowed to repeat yourself. Okay? There is no path from A to G, so A and G are not connected. In other words, they're in different components. So you can think of this notion of connectivity as a kind of equivalence relation on the vertices. 2 vertices are equivalent. The actual adjective is connected if there's a path from one to the other. And the components are the equivalence classes for this equivalence relation. Some people will sometimes say connected components. That's redundant. By definition, components are connected. Okay. Now, we're going to talk about connectivity, reachability, and so on as an algorithmic problem. Given 2 nodes, how do you tell whether one is connected to the other? Given a graph, how do you figure out how many components it has and what they are? As algorithmic problems, it sort of will be the punchline of the lecture today. But for now, I want to stick to talking about graphs as structures. Okay. Now, I do want to emphasize that this is not really a graph. Okay, in the same sense that this is not really the number 3. It's a representation of the number 3. Any more than a regular expression is not itself a set of strings. It's a representation of a set of strings. In this kind of representation is usually referred to as a drawing or as sometimes as an embedding of the graph. But if we really want to be formal about this, what a graph is it's a pair of sets. There's some non-empty finite set, which we'll call V, and whose elements we will refer to as vertices and nodes. Okay, these are the vertices. And a set E of pairs of vertices, which we will call edges. And again, to be formal, I need to distinguish between 2 kinds of pairs. Right, so in an undirected graph, a pair is just a set containing 2 vertices. And in a directed graph, a pair is actually ordered. There is a first vertex in the edge, and there is a second vertex in the edge, which are often referred to as the tail and the head of that directed edge. Now, to save some notation, normally I will write undirected edges just by gluing the 2 vertices together, and normally I will write directed edges by having a little arrow pointing from the tail to the head. Okay? So, Just like when we were talking about strings and languages and so on, what is an alphabet? An alphabet is an arbitrary finite set. To make it interesting, non-empty. What are the vertices of a graph? An arbitrary finite set. What are the edges of the graph? An arbitrary collection of pairs of those things that we called vertices. Okay, so for example, I can define a graph over the set of people in this room. Each of us is a vertex in this graph, and I will draw an undirected edge between two people if they know each other's name. Okay? Or I could define it as a directed graph from person U to person V if U knows V's name. Hopefully this means that there are lots and lots of edges coming into me, certainly quite a bit more than there are edges going back out to you. But this is a graph. It's not a collection of circles and lines on a piece of paper, although we could, in principle, figure out how to draw that. It's this much more abstract thing defined over, it's essentially some kind of binary relation over an arbitrary finite set. So if I really need to emphasize this layer of abstraction, because exactly the same graph may show up in lots of different representations, and it's important not to confuse the representation, for example, the data structure that you're given, with the actual graph. So here is another drawing of exactly the same graph. The same vertices with the same labels with the same edges. Now, the difference between the drawing that you saw earlier and the drawing that I'm putting up here now is in the original drawing I had this pair of edges that crossed each other, and in the new drawing all of the edges are disjoint except where they meet at the endpoints. Right? So this particular drawing of the graph shows that the graph is planar. This is an adjective that means I can draw it on a piece of paper where the nodes are represented as little circles and the edges are represented as curves that don't intersect. Okay? So this is a planar drawing or a planar embedding. And because it's the same as this graph, this is a planar graph. Okay? The drawing is not the graph. Just because I have a non-planar drawing, because of that crossing, that doesn't make it a non-planar graph. Okay? Not every graph is planar. You might have seen some discussion of Euler's formula back in 173. Euler's formula is near and dear to my heart, but we don't have time. Here's another drawing of the same graph. The vertices are line segments. The edges are intersection points between those line segments. Every intersection point is defined by two segments, exactly. So in this drawing, which is sometimes referred to as something I can't spell, an intersection graph, right? I've reversed the roles of the things that look like points and the things that look like lines. In this case, it's the lines that are the vertices, and it's the intersection points between those lines that represent the edges. Again, I mean, this example is straight out of the lecture notes. You can check, there's an edge between A and B. Okay, there's an edge between segment A and segment B. Here, there's an edge between C and E. Sure enough, there's an edge here between segment C and segment E. And it's possible that when you're asked to describe, to solve a problem that ultimately you want to solve using a graph algorithm, the representation of the graph that you might be given is a bunch of segments in the plane, meaning an x and y coordinate for one endpoint and an x and y coordinate for the other endpoint. And so you just have this list of 4n numbers, and it represents a graph. Okay? Here's yet another representation of exactly the same graph. This is the same representation that I talked about yesterday when we were talking about greedy algorithms. You can think of each of these boxes. This is each of these boxes represents an interval on the real number line that has a left endpoint and a right endpoint. Maybe this is the starting time and the ending time of some class. So the vertices in this case are classes, and there's an edge between two classes if they conflict with each other, if they meet simultaneously, if there's any moment where both classes are meeting. And again, you can check by brute force that I really am defining the same binary relation between the same objects with the same labels. It's just that I'm using different objects in a different binary relation than I was using before. Okay? So it's wonderful to think of the circles and lines as a graph, but keep in mind that that's not the only way to represent graphs. It's not the only way even to gain intuition about graphs. Sometimes by changing the representation, you can reveal some additional structure that you wouldn't necessarily see otherwise. Okay, so I'm going to show you another graph that you've seen before. Okay. I'm not going to go through the whole thing. I'm just going to write down a couple of the cases here. Okay, so this is the bulk of the recurrence for, in fact, this is the recurrence for computing the edit distance between two strings. Here, edit ij, again, this is straight out of the notes. Edit ij is the number of insertions and deletions and replacements that I need to perform to transform the first I characters of string A into the first J characters of string B. Okay, and in class, we turned this recurrence into a dynamic programming algorithm that memoized the values into an m by n array, and the way that we developed the algorithm is by thinking about dependencies between slots in that array. In other words, we would be playing with a graph. The nodes of that graph are all possible subproblems that we might have to evaluate in order to figure out this edit distance. In other words, the nodes of the graph are the cells in that memoization array. And there's a directed edge from one cell to another if, in order to compute the value in one cell, I need to have already computed the value in the other. Right, so I have some sort of 2D array, and for each spot in the array, I'm going to have edges from previous column, same row, previous row, same column, previous row, previous column. Okay, all right, that was a little useless, but for every white square, I'm going to have edges from the 3 black squares surrounding it. Okay, so this is a graph that has mn vertices and approximately 3mn edges. And when we talk about doing dynamic programming, what we're really doing is we need to find a way of sorting the vertices of the dependency graph so that all of the edges point from earlier nodes to later nodes. Now, because of the special structure of the dependency graph in this case, we can do that just by having a pair of nested for loops over the 2D array. Maybe the outer loop goes column by column and the inner loop goes row by row. That's good enough to give us a proper ordering of the problems in the dependency graph. But there are problems for which the dependency graph that you get is not so well structured. And in that case, you have to apply a slightly different algorithm to get this ordering of the subproblems that respects each of the dependencies. That more complicated algorithm is called topological sort. And we will see it on Tuesday. Okay? It's essentially just depth first search. So congratulations, we've been doing depth first search for 2 weeks. Okay, just over very, very highly structured graphs. Now there's another graph that's actually quite closely related to dependency graphs, which we've played with even earlier. These are recursion trees. Right, so you have a problem, and it calls itself recursively 3 times, and each of those things call itself recursively 3 times, and so on. Again, you have a node in this tree. A tree is just a graph that's connected and doesn't have any cycles. Each of these nodes corresponds to one of the recursive subproblems that you evaluate, and you have a directed edge, which here I'm indicating the direction by drawing the tail above the head. So these edges are all directed down. That indicates that when I called this subroutine, it made a recursive call with these parameters. It made a recursive call with those. Okay, so each of these downward edges corresponds to a recursive call. Okay. Now, of course, this recurrence itself has a recursion tree. It defines a different graph than this dependency graph. Because in the recursion tree, you might have 2 different nodes that correspond to the same input parameters. So again, what dynamic programming really is taking this recursion tree and folding identical nodes together. Okay. And then doing depth first search. I'll give another example. Okay, a configuration graph. So this was actually the very, very first example that we saw of a recursive algorithm. Tower of Hanoi. Okay, so the Tower of Hanoi problem, once you fix the number of disks, implicitly defines a graph where the vertices of the graph are all legal configurations of the disks, by which I mean, every disk needs to be on one of the 3 pegs, and they need to be in sorted order from smallest to largest on each peg. And each of the edges corresponds to a legal move. For example, moving this disk over to the first pole. Now, it turns out for the Tower of Hanoi problem, once you do a move, you can immediately undo it. So, in fact, I should think of this as an undirected graph. You can think of it as a directed graph with directed edges pointing both ways, but you might as well just think of it as an undirected graph instead. And then I can show you what that graph looks like for 3 disks. It looks like that. That's 4 disks. Okay. Some of you might recognize this as a Sierpinski triangle, as a nice little fractally thing. It's a triangle made up of 3 smaller Sierpinski triangles connected by edges. So in this picture, I've colored the disks red, green, blue, and gray. And correspondingly, each of the edges has a color depending on the color of the disk that I'm moving. Every one of those vertices corresponds to a particular configuration of the disks. Every edge corresponds to a legal move. And the basic problem for the Tower of Hanoi puzzle is to get from the lower left corner, which corresponds to all disks on stick 1, to the lower right corner, which corresponds to all disks on stick 3. In this formulation, the solution is pretty easy. You just run along the bottom of the triangle. Now, in the homework, we saw a variation of the Tower of Hanoi problem where you weren't allowed to move anything directly between 1 and 3. And if you look at the configuration graph for that variant of the puzzle, it has the same set of vertices, exactly the same set of configurations. The disks can be in exactly the same places. But in that case, from any configuration, you have exactly 2 legal moves, except for the starting and ending configurations where you have exactly 1. And for that particular puzzle, the configuration graph turns out to be a path. And then the solution is, again, really easy. Do the only thing that you didn't just do. Okay. Now, thinking about the Tower of Hanoi puzzle in this particular form may not be the most fruitful way to do it, but it does provide, mostly provides an illustrative example. Another kind of configuration graph that you might consider where really you do want to think of it as a graph problem is various kinds of games and puzzles. Right, so there are all sorts of puzzles. You can go down, believe it or not, there are at least 2 stores in Lincoln Square Mall where you can buy these things. Or these puzzles where you have various oddly shaped pieces that you have to put together into a whole. You can think of the configurations of those pieces as nodes in a graph, and the various moves, like I'm going to slide this stick, a 1/4 of an inch one way or the other, as an edge. Or you can think of chess as a big graph where the nodes are legal positions and the edges correspond to legal moves. And when you're trying to solve these puzzles or playing these games, really what you're doing is trying to reason about how to walk around in this graph. Okay. Another one that we've seen already zero, one, zero, one. Okay, so this is a DFA. Formally, it's a collection of states. A specification of one of those states as a starting state, a specification of a subset of those states as accepting, and a transition function that tells me, given a state and a symbol, what is the state that I should go to when I read that symbol. But at another level, you can think of a DFA as a directed graph, where each of the vertices corresponds to a state, each of the directed edges corresponds to a transition, and the edges are labeled according to, with the symbols that make that transition happen. Okay, so this edge from S to U is labeled 1 to indicate that delta of S comma 1 is equal to U. Right? But I can actually do this transformation going backwards. Given a directed graph with labeled edges, as long as I satisfy the right conditions, I can translate it back into a DFA. And the condition that I need is that every vertex and for every symbol, there's exactly one outgoing edge with that labeled with that symbol. Okay? So a DFA is a graph with some conditions. Right? Not every graph actually qualifies. Or not every labeled graph. Now, I'm attaching some extra information to the edges in this case, but it's useful to think about this not as, the symbol, as a big table. The way this might actually be represented in memory is that I have a big table indexed by states and symbols, and for each entry in this table, it tells me, what the value of the transition function is. That's a data structure, but the abstract object that it represents, I might as well think of as a directed graph. An NFA is, of course, just a labeled graph without those conditions. So an NFA is a directed graph where the vertices correspond to the states and the edges correspond to transitions, and an edge from U to V is labeled with symbol A if it is possible to transition from U to V on reading the symbol A. Right? Now, in this particular case, I still have a DFA, but if I add, for example, this transition on the side, and maybe get rid of these transitions in the middle, now I have an NFA that we've seen before. This is the set of all. This accepts the set of all strings that contain either 0, 0 or 1, 1 as a substring. It's a graph. And when I want to think about problems involving DFAs or NFAs, often the way that you solve those problems is to say, think of the machine as a graph and run the following standard graph algorithm. So for example, if I'm given an NFA and I want to know whether it accepts anything, how would I do that? It's maybe going a little bit, looking a little bit ahead, but can you just make a guess? Depth first search will work. Okay? If I want to know whether this NFA accepts anything, what I'm really asking is it possible to get from S to an accepting state by following transitions? In other words, is it possible to get from node S to one of the accepting nodes by following a sequence of edges? Right? If the graph were undirected, I would say, is S in the same component as some accepting state? In the case where the graph is directed, the word we use is reach. So can S reach an accepting state where reach means that there's a directed path from S to V. And the algorithm that you use to answer this reachability question, can I get from point A to point B, is, well, one of the algorithms you can use is depth first search. Right? The way that I will actually properly answer that question in 45 minutes, the correct answer is whatever first search. Doesn't have to be depth, doesn't have to be breadth, doesn't have to be random, doesn't have to be, prettiest first. It's just whatever. Okay? And by whatever first search, I actually do mean a specific algorithm. Now, there's one last thing I want to point out here, is that sometimes when you want to solve a problem using a graph algorithm and the world very helpfully hands you a graph, the world may not be as helpful as you think. It may not actually, you may not want to run that algorithm on the graph you were given. You may want to run that algorithm on some graph that you derive from the graph that you're given. So a good example of this is if you're given an NFA, there's this thing called the subset construction that gives you an equivalent DFA. Right? And there are questions that you can ask which are much easier to answer if what you're handed is actually a DFA. If you think about the graph that you want to search as being the DFA rather than the NFA. But it could be that you were given the NFA. Okay? So, again, I want to, emphasize that this does not necessarily require you to do this construction. Right? You may be able to answer the question using an algorithm designed for DFAs, even though what you're given is an NFA, which may be exponentially smaller. And so I will define the vertices of the graph that I care about. The vertices of the graph are all subsets of states of the given NFA. Right? And the edges of the graph are, let's see, well, I'm going to imagine I'm going to ignore the labels for the moment. There's an edge from subset A to subset B if for every node U in the beginning there is a node V in the end such that there's a transition in the NFA from U to V. Okay, this is a summary of the subset construction, ignoring for the moment the labels. Okay, which means, for example, this is a 16-node graph. This is a representation of a 16-node graph. The vertices are the empty set, this, these two, this, these two, these three, and so on. Okay? The graph that I'm thinking about is not necessarily the graph that's drawn on the screen. It's some other graph. Right? Now, when we were talking about actually converting NFAs to DFAs, there was an incremental version of the subset construction algorithm, where you start by saying, well, I know that the equivalent DFA is going to contain the set containing S as its start vertex. And now I start exploring outwards, building up, discovering new states in the DFA. What that algorithm was doing was running breadth first search on this DFA here, but doing it by manipulating the NFA. Okay? So you were given, in effect, one graph, and the algorithm, the incremental subset construction algorithm, was running an algorithm implicitly on a different graph. Now, we'll see more examples of this in lab tomorrow and in the homework, but it really is important to keep in mind that they say, here's a problem, it's probably going to be solved with a graph algorithm. The first graph that pops into your head might not be the right one. Okay? You need to somehow think, is this really the graph that I want? Right? And so when you're solving a problem using a graph algorithm, you need to write down a sequence of sentences. I mean, this is sort of boilerplate, like you write down the following things when you do an induction proof, you write down the following things when you do a dynamic programming algorithm, you write down the following things when you want to apply a graph algorithm. Tell me what the vertices are. Tell me what the edges are. Tell me what problem you want to solve on that graph. And don't just say the problem. Right? And don't say Dijkstra. Dijkstra is not a problem. Well, at least not for us. Shortest paths is a problem. I want to compute the shortest paths from this node to that node. That's a problem. Dijkstra is an algorithm that you can use to solve that problem, which is, of course, the step that you say next. And then finally, you need to give the running time, but in terms of the original input. Okay. Now, when we talk about graph algorithms, I'm always going to be analyzing the algorithms in terms of the number of vertices and the number of edges of the graph. But you may not be given the graph. You may be given a Tower of Hanoi puzzle or a Rubik's Cube or an array with a bunch of numbers in it, or 2 strings, and you derive a graph from that and say, well, and then I run this standard graph algorithm, and the running time is phrased in terms of these variables v and e, you need to translate that running time back to a function of the actual input that you were given. Because the user, the person who said, build a box to solve this problem, isn't going to know what v and e are. Okay. Again, you'll see this at the top of the page tomorrow in lab. Okay. So, any questions about what a graph is? All right. Now, the next question is, you know, when we want to think about designing graph algorithms, it is really useful to imagine that we really are given the graph that we want to search or manipulate or do whatever. Okay, so, you know, there are a lot of problems that start out like this. Given a graph, do something. What does that phrase actually mean? Right, now, when we're designing algorithms, remember, we're aiming to actually write code. And when we say given a string, we can easily imagine what that means. It's an array where in every slot in the array there's a symbol from some alphabet that we understand as being fixed. It means it's a 7-bit ASCII value, for example. Arrays are nice and comfortable and simple, and everybody knows what they are. Right? So there's no confusion when I say given a string. But a graph is a somewhat more abstract object. And so when I say given a graph, I have to nail down exactly what that means. What does it mean to be given a graph? What pattern of bits in memory is going to represent the graph? There are 2 standard representations, both of which you've already seen, not necessarily in this class, but somewhere. Can somebody tell me one of them? Yeah. Okay. There's a data structure called an adjacency list. Now, an adjacency list is an example of a principle sometimes called the red herring principle. In mathematics and in computer science, a red herring is not necessarily red and it's not necessarily a fish. An adjacency list is not a list. It's an array of lists. Okay, so the idea, at least for the standard textbook adjacency list data structure, is you start off with an array indexed by the vertices. 1 slot for every vertex, which means you already somewhere have an implicit map from the vertices to the integers from 1 to n for some integer n. And then for every vertex, you have a list of all of the edges with that vertex as an endpoint. And typically, for example, you know, if this is vertex 2 and there's an edge from vertex 2 to vertex 4, what I'll store in that edge record, in addition to the pointer out to the next edge, is the other end of that edge. Which means somewhere here in vertex 4 in this list, if this is an undirected graph, I will have an edge record labeled 2. Okay? And now, so this tells me that there's an edge from 2 to 4, and there's an edge from 4 to 2. If this is an undirected graph, I need both of these so that I can navigate in either direction. If this is a directed graph, I might have an edge from 2 to 5, but no edges leaving 5, in which case I would just have a null pointer there, an empty list hanging off of 5. Okay? Now, why is this data structure useful? The capabilities that you get from an adjacency list, first of all, you can access any node in constant time. right? You have a pointer to a node, bang, you just jump right into the data structure, and you can start looking at the edges. You can list edges at each node in constant time each. Right, so for example, if I want to say, okay, in the middle of my algorithm, I'm going to have a variable v that stands for a vertex, and then I want to say for all edges vw, incident to v, do something. I can implement that for loop just by scanning down this list. All right, under appropriate conditions, I can do some modification to the graph. If I want to insert a new edge between two vertices u and v, I need to insert something into u's list, and I need to insert something into v's list. If I want to delete an edge between u and v, however, I have to figure out in u's list the edge record that corresponds to the edge uv, and I have to scan through v's edge list to find u. Okay, so maybe deletion. Okay. The one thing that's kind of hard is to ask just a simple question. Here are two vertices. Are they connected by an edge? Now, the nice thing about most of the algorithms that we're going to see is that, in fact, you never need to ask this question. It's a little bit surprising if you were just going to design a graph algorithm from scratch. That the basic question like, is there an edge here, is not something that you actually need to worry about. But it turns out you don't. Nevertheless, sometimes people do design algorithms using adjacency list where you do need to be able to delete things. You do need to be able to look at a pair of edges and decide quickly whether they're connected or not. And in this case, the adjacency list data structure is a little bit inefficient. But it's inefficient for a really stupid reason. And now I'm going to ask a somewhat provocative, open-ended question. Why are these linked lists? If I really wanted to be able to insert and delete things more quickly, maybe it would be better to use a different data structure here to store the list of my neighbors. For example, I might store the list of my neighbors in some sort of balanced binary tree, and then if I want to see whether I'm connected to somebody, I only have a logarithmic, binary search that I have to do instead of a linear search. Maybe, even better, I could just store all my neighbors in a hash table, and then if I want to see whether I'm connected to somebody, I just roll the dice to get the hash value and look in that spot in the array, and well, there it is, I'm done in constant time. Modulo the usual hand waving that everybody does over hashing. Okay, so, and moreover, you can design these data structures so that they don't use up a lot of extra space. A good implementation of hash tables, you don't waste more, the amount of space that you use is at most twice the number of things that you're storing in the table, which is already true here because for every edge, I need to store the name of the vertex on the other end, and I need to store a successor pointer. So in terms of memory efficiency, there's really no reason to use linked lists. And in terms of time efficiency, there are negative reasons. There are reasons not to use linked lists. So why is it then that if you go to Wikipedia, or if you look in any textbook on the planet, it tells you to use a linked list? Why did you learn to use a linked list in CS225? Anyone? Yeah.
Easy to implement.
Okay, good. It's easy to implement. That's one reason. On the other hand, once you've implemented hash tables once, hash tables are really easy to implement. You have the library, you invoke it. It's the same number of lines of code, insert. Well, it calls the insert method for the hash table versus the insert method for the linked list. So, yeah, a little. If you were really building the world from scratch, okay. I would argue that, one of our goals as writing code is to make it easier on the user before making it easier on ourselves. And by using the hash table, yeah, it's a little bit more work, but it pays off. So, yeah, maybe. Anyone else? Yeah.
Maybe something related to graphs.
I'm sorry?
Something related to graphs.
Something related to graphs. So there are applications of graphs where it is actually important to have an ordering on the edges incident to a vertex. In fact, that's actually, if I want to think about drawing graphs in the plane, the way the underlying data structures for this thing work is that at every vertex, I not only know what the edges leaving the vertex are, I actually know what order they are in or surrounding the vertex. And just that ordering is enough to describe this drawing up to, wiggling things around. As far as the topologist is concerned, that's enough to specify the drawing. But there are other ways of encoding that ordering that also use more efficient data structures than just linked lists. So, yeah.
Insertion is quick.
Insertion into a hash table is quick. It's not as easy to do it quickly. You have to do a little bit of balancing to make sure the hash table doesn't get too full, but that's easy. When the hash table gets too full, you make it twice as big and rehash everything. And that won't happen very often, and in the end, it all washes out. Yeah? Same if you do depth and breadth are the same, or depth and breadth are the same if you
had a hash table.
Right, so for the basic, so this is the first major reason, actually. This is good enough. Right, for the algorithms that we actually want to talk about, this is enough to get the most efficient. We don't get any speed gains on doing depth first search. We don't get any speed gains in doing Dijkstra's algorithm or Kruskal's algorithm by having this more efficient data structure. So, okay, this is fine. We don't need to do any more work. We're lazy. Let's go home. The other reason why it looks like this is because it's always looked like this. The reason why it looks like this in 225 is because this is the way it looks in CLRS, the big honkin' algorithms book from MIT. The reason why it looks like this in CLRS is because this is what it looked like in the textbook that Corman used when he was an undergraduate, and that Leiserson used when he was an undergraduate, and that Revest used when he was an undergraduate, and that Stein used when he was an undergraduate. That book was probably the one written by Aho, Hopcroft, and Ullman. The reason Aho, Hopcroft, and Ullman have it as a linked list is because Knuth said it should be a linked list. The reason Knuth said it should be a linked list is because it was easy to implement. Why not? It's tradition, nothing else. There is no reason, there is no implicit reason at all to have this be a linked list, right? This is, this is what we need to be able to do, and so fine, a linked list is an easy way to do that, but there's absolutely no reason why the linked list should be implemented with successor pointers as opposed to being implemented with, say, a hash table or something else. I do want to point out one other data structure that is very common and suffers from exactly the same problem. And to show you that data structure, I need to do this. Does anybody recognize this as a picture of a data structure? What is that? For some reason, graphs, the lists are always drawn left to right, and in this other data structure, they're always drawn down.
Like a linear chain hash table?
Yes, this is a hash table with linear chaining. Why do we do linear chaining into linked lists? Because we always have. No other reason whatsoever, right? So if you come to 473++ next semester, I'll explain exactly how you get away with really doing hashing in constant time. Among other things, by not doing that. Okay, So that's one graph representation. For every vertex, I keep the vertices in an array, and for every vertex, I keep some data structure that stores the incident edges in a form that allows me to list them quickly. Think of it as a linked list if you want. But that's not the only data structure that people use. I wouldn't think of the other one. An adjacency matrix. Okay? Okay, in this case, you have this big matrix whose rows are indexed by vertices and whose columns are indexed by vertices. And there's a 1 in row U, column V, that indicates that UV is an edge. And there's a 0 in row W, column X, that indicates that WX is not an edge. If the graph is undirected, this matrix will be symmetric around the main diagonal. If the graph is directed, then you have to say, okay, the row indicates the tails of the edges and the column indicates the head of the edges. And so now this means there's an edge from U to V, but there's not an edge from W to X. Okay. Now, adjacency matrices have, remember, matrices, singular matrix, have the nice feature that you can look up a vertex in constant time. Or, sorry, you can look up an edge in constant time. I want to know whether U and V are connected. I just go to row U, column V, one memory access, I'm done. On the other hand, if I want to list all of the neighbors of a vertex U, I have to spend order V time. I have to do a linear scan, even though the number of edges that I'm listing might be much smaller than the number of vertices. Okay. Similarly, if the graph is very sparse, if the number of edges is fairly small, this data structure is always going to use a quadratic amount of space, whereas this data structure, the space is going to be the number of vertices plus the number of edges. And so if I have a graph with only, say, 3V edges, this gives me a data structure where the size is linear in the number of vertices, whereas an adjacency matrix gives me something that's quadratic in the number of vertices. Now, a much more subtle question is, I just spent the last 5 minutes ranting about the fact that, in fact, if you use the right data structure, you can do interesting things within an adjacency list data structure in constant time, like check whether a node is there or an edge is there, insert or delete edges, all this stuff by having secondary hash tables instead of linked lists you can do in constant time, which is normally touted as the advantage of having an adjacency matrix. So in terms of time complexity, if I use the right secondary structures in my adjacency list, there's no advantage to adjacency matrices at all. Anything I can do in an adjacency matrix, I can do at least as fast using an adjacency list and using no more space. So adjacency matrices are bigger, adjacency matrices are slower. So why use them? Why talk about them? I'm sorry? Yeah, they're definitely easier to implement. That's true. Okay? That's not a real reason. This is the big leagues. We are computer scientists. We're not afraid of implementing a data structure. Yeah?
I may be way off, but I think it's actually the right thing to use.
Okay, so if the graph is really dense, this in practice actually is faster to use an adjacency matrix data structure. There is a certain constant amount of overhead involved in chasing through these pointers and in manipulating the data structures if I want to insert and delete things. And so if the graph is dense, yeah, I really do want to use an adjacency matrix in practice. The flip side of this is if you've taken or thinking about taking 450, or you might have even seen this in CS357, there are data structures that effectively represent sparse matrices. Right? So even if the matrix is sparse, I don't necessarily really have to implement it as a 2D array. I can do something much more interesting. All right. There's another reason why I might want to use adjacency matrices, which is that some of the things that you do with graphs, you're really doing linear algebra. This is why it's called an adjacency matrix and not an adjacency array. This really is a matrix, meaning it really does correspond to a certain linear transformation that has interesting properties. And so it's useful to think about it because, for example, PageRank, the thing that Google computes, is the most significant eigenvalue of the adjacency matrix of the web. That's what PageRank is. Right? You take a matrix defined by the web graph, where there's an edge from U to V if U has a link to V without a nofollow attribute. You take this enormous honkin' matrix and you do some linear algebra to it, and out pops a number for every row. That's the principal eigenvector of that matrix, and that the coefficient corresponding to each web page is its PageRank. That is what Google uses modulo politics to rank its web pages. Okay? The other reason why you want to think about sometimes adjacency matrices is that maybe the graph is not given to you explicitly. Maybe it's given to you as sort of an implicit relation between other things. And now if you design your algorithm for adjacency matrices, you can use it for intersection graphs of segments, for example, by saying wherever the algorithm would look up in the matrix whether these two vertices are connected, instead, I will do the constant amount of computation required to figure out whether these two line segments intersect. Right? So adjacency matrices are arguably not as useful as explicit representations of graphs. But nevertheless, designing algorithms to use them allows you to run those algorithms on implicitly represented graphs, where there's some relation that you need to call a subroutine to figure out whether two things are related or not. Okay? So most of the time we really are going to stick to adjacency lists, but it really is useful to remember, hey, there's this other representation that might actually be better to think about depending on exactly how the graph is given. Okay. All right. Okay. So the last thing that I want to talk about in the last 10 minutes is how to traverse a graph, meaning how to, traversal is a standard thing that one does with graphs all the time. Perhaps the simplest version of traversal, the simplest application of traversal I can think of is you have a data structure with a bunch of pointers in it, and you'd like to print it out. Okay? That means you need to visit every record in this pointer-based data structure, but you only need to visit it once. You don't want to repeat yourself, especially if there are cycles in your data structure. If you don't do some bookkeeping to keep from repeating yourself, you'll end up falling into an infinite loop. Let me show you. I think I'll just put the lecture notes up on the screen rather than trying to write these things down. The sort of canonical graph traversal algorithm is depth first search. Right? This is the first graph traversal algorithm that people think of. I know this because this was the first graph traversal algorithm that one of you thought of about half an hour ago. And the way depth first search works in its usual recursive formulation is the following. I start out by at some particular vertex, and in pre-processing phase, I make sure all of the vertices are unmarked. So I'm going to have an extra bit stored somehow with each node in the graph. And whenever I call the recursive DFS on a vertex V, first, I check to see whether the vertex is marked. And if it is, I'm done. I've already been here. I've already printed this record. I don't need to do it again. If it's not, then I will do whatever it is I'm going to do with that node. But among other things, I mark the node. And then for all edges leaving that node, for all neighbors, I recursively search through those neighbors. Now, the marking the vertices guarantees that I'm going to visit each vertex and actually do something at most once. I'm also in this for loop, when I run the algorithm on a big graph, this for loop here is going to be executed once for every vertex v, which means I'm going to look at each edge in the graph exactly twice. Once from one end and once from the other. Okay? The first time I visit an edge, for example, I might visit v, look down and see that w is unmarked and recurse in w. The second time, I might visit w, and I look back at v and notice that it's already marked, and then I don't visit v again. Okay? So the running time of this algorithm, this recursive algorithm, is proportional to the number of vertices plus the number of edges. Every vertex, I spend a constant amount of time checking to see if it's marked and marking it. And for every edge, I spend a constant amount of time, the constant is 2, glancing down that edge and recursively calling DFS at the node at the other end. Okay. Now, like any other recursive algorithm, and I'm going to violate one of my cardinal rules here, I'm going to actually pretend that I know how recursion is done and not by magic. Really, recursion is implemented by a stack. And so you can turn DFS into an iterative algorithm by maintaining the stack yourself. Right? And so the way this would work is you pass in the start vertex where you want to start the depth first search. You push it onto the stack, and as long as there's something on the stack, you pop the top thing off, check to see if it's marked. If it's not, mark it, and then push all of its neighbors onto the stack. And notice this might push a vertex onto the stack more than once, but on the first time that the vertex is popped off, you'll do real work. And the second time, and the third and fourth and seventh time it's popped off, you'll say, yeah, and just throw it away. The number of times that you push is going, assuming the graph is connected, is going to be proportional to the number of edges. Therefore, the number of times you pop is going to be proportional to the number of edges. Because you can't pop more than you push. That's how stacks work. The two algorithms are actually just identical. They do exactly the same thing. Just I've done one with a data structure instead of with recursion. So both versions of this algorithm will run in time v plus e. But now once I have a data structure here, a stack, I don't have to stick to it. Right? So here is a, see if there's a way to zoom in here. Oh, bother. No. All right, fine. There's a more generic traversal algorithm that uses a data structure I will call a bag. A bag has the following methods attached to it. I can ask the bag if it's empty. I can put things into the bag, and I can ask the bag, hey, give me something. A stack is a bag that is first in, last out. A queue is a bag that's first in, first out. A priority queue is a bag that's whatever in, lightest out. A random bag is it rolls a die and hands you something random, whatever. I don't care what the bag is. And then all I have to do now is just replace the stack in my earlier iterative DFS algorithm with bag operations. And now I have a generic traversal algorithm that I refer to formally as whatever for search. I don't care what order I visit things. I just want to make sure that I visit every vertex in the graph exactly once. Now, if I play with this graph, play with this algorithm a little bit more, I can get some additional information out of the search. Namely, I can assign to every node a parent that essentially is, who do I blame for waking me up and making me do work? So imagine now every node is a person, and we're going to do this whatever for a search, but putting things into the bag, the way I'm going to do that is I have to call all of my friends. Right? After I've done that, later if the phone rings, I can ignore it. I've marked, I've done my job. So what the parent node says is, whenever you phone your friend, they go into the bag, but they remember who called them. When you pull a person out of the bag, that person remembers the node, the first part of this ordered pair that I push on, remembers, hey, why was I put in this bag? Oh, it was because Jeff called me, the bastard. It's his fault. Okay? So everybody points up, everybody blames somebody for putting them into the bag. This collection of parent pointers defines a spanning tree for the graph. Everybody blames another node except for the starting node, which doesn't have anybody to blame. Okay? And so this gives you a way of building a spanning tree of the graph. Okay? It's not necessarily a minimum spanning tree. It's not necessarily a shortest path tree. But it is a spanning tree. And if you look in the notes, you'll see an actual proof. Okay? Now, if you're down at the bottom of the screen, we'll look at this and then we'll be done. A depth-first search using a stack tends to build spanning trees that are long and skinny, which is why it's called depth first. You tend to, depth first you could think of as sort of me first. Okay, you say, I'm going to recurse on one of my nodes, and immediately that neighbor wakes up and starts recursing on its neighbors, and immediately that neighbor wakes up and starts recursing on its neighbors. And so the blame graph, if you will, the spanning tree very quickly gets very deep and very skinny. A breadth-first search, on the other hand, where you use a first-in, first-out queue for the bag, think of this as like the laziest possible graph search you can. You don't wake up until absolutely everybody who was put in the bag before you. You tend to get these short, bushy-looking trees. And in particular, you get trees that contain the shortest paths, meaning the fewest edges from the start vertex to every other node in the graph. If all you want to do is decide whether a graph is connected, you run whatever first search, and then you see if this other node is in the tree. If what you want is the shortest path between two nodes, then you need breadth first search, not whatever, because the actual tree matters. And then minimum spanning trees or breadth first, more general shortest path trees, you can think of them by using a particular kind of priority queue for the bag. And that's all I have to say. Some of you have given me midterms because you had a regrade request. I will get those back to you. I'm sorry that I haven't gotten them back to you yet. They'll be back in your hands tomorrow in lab. If you do have a question about regrading the midterm, please try to get those to me as quickly as possible. Thank you.